What I'm going to go over now is how to solve for the um, values of resistance, current, and voltage for series and parallel resistor circuits. To begin, I'm going to draw a battery here. We'll call this 12 volts, and it's going to be attached to 3 different resistors. There's my first resistor, my second, and my third. It's not really overly important to be perfect with how we draw those. I'm going to call this R1, and I'll say that it has a resistance of 5 ohms. And ultimately, I'm going to want to solve for what the current through that is, and also the voltage across it. So basically all the information about what's going on with that resistor. The second one we'll say is 8 ohms, and we'll search for, again, the, the current through that one and the voltage. And then same thing with the third one down here. We'll say this is 7 ohms, looking for current 3 and voltage 3. Okay, so to begin, one thing that I know from Ohm's law is that voltage is equal to current times resistance. So this equation is going to be kind of essential to solving for these missing variables. The problem right now is I have 3 different resistance values. And again, while it might seem like a good idea to just jump right in and say, well, it's 12 volts for each one, we do have to remember that the 12 volts here is for one complete loop around this circuit. And so the sum of the voltages should be 12, but no individual resistor is going to have a difference, electric potential difference of 12 volts. So I can't just make that assumption. What I'm going to need to do is combine these, and first remind myself that what I'm combining are 3 resistors that are in series, and then I'm going to redraw this. So I have 12 volts, except now it's going to be attached to one equivalent resistor. And that's going to have a resistance value, which we'll solve for in a second, one single current, and a voltage of 12 volts. The reason I know it's 12 volts is because an electron that passes through this resistor will have made the full jump from one side of the battery to the other side. So it's going to be the full 12 volts. Now back to the fact that this is in series. In series, the equivalent resistance is given by the equation R1 plus R2 plus R3. And the reason why that occurs is because if you imagine an electron has left the battery and is traveling through this circuit, it has to go through the first resistor, which is going to be offering resistance, slowing down the electron. Then it has to go through the second resistor, which is offering even more resistance. Then it has to go through the third one, it's offering even more resistance. And so when they're in series like this and each electron traveling through the circuit has to go through all 3, it's going to be kind of adding up how much resistance there is. So to do this, do some heavy math here. 5 plus 8 plus 7 gives me 20 ohms. And now I'm kind of all set to go to solve for my current in this circuit. And what I do is go back to my V equals IR. I'm solving for I, so I is V over R. 20 divided by 12, type it in your calculator, you end up with 0.60 amps. And that's my current through the circuit. So as the electrons are traveling through the circuit, they do so at 0.6 amps. Amps, again, is a measurement of how much charge per second is being delivered. What I can do here is I can bring back certain pieces of information with me back to my original diagram. Considering resistors in series, one thing that I know is that the current is going to be the same for all of them. The reason for that is because I only have one pathway that electrons can follow. There's only one set of wires that they can go through. And so just like how if you only had one lane on a highway, but it was packed with cars, you can't have some cars going 60 miles per hour and then cars in front of them only going 40 miles per hour. Obviously, they'd be bumping into each other and piling up, and electrons don't do that in wires, just like cars don't do that on the highway. And so instead, what we have is just one single speed. And so all of the current through this wire is going to be limited to 0.60 amps for all 3 resistors. And what that means, as you might expect, is that I can now solve for my voltage value for each one. So solving for resistor number 1, we have 5 times 0.6, which gives me 3 volts. For resistor 2, I do 8 times 0.6, which gives me 4.8 volts. which I had here, 4.8 volts. And for resistor 3, I do 7 times 0.6, which gives me 4.2. One final step, now that I have all my data, is just to do a quick check. And if I follow one loop around this circuit, I get 4.2 volts plus 4.8 volts, which gives me 9 plus 3 volts, adds up to 12, which is exactly what I expected. Solving now for resistors that are in parallel. I'm going to keep it simple. We'll just have two resistors. In a parallel circuit. We'll call this 12 volts. Resistor number 1 is 3 ohms. Resistor number 2, 6 ohms. I'm going to solve for the current in each of those and the voltage in each. In this case, I'm going to kind of overcomplicate it just real quick as I explain what the kind of normal pathway for solving these types of problems is. I'm going to do that because I know that V equals IR, but I have two different R values, so I have to consolidate. And I'm going to call this parallel here because they are in parallel. And I'm going to redraw this with only one resistor, 12 volts. And in this case, with resistance, the equivalent resistance is given by the equation 1 over R1 plus 1 over R2, which when I do that for these two resistors, 3 ohms and 6 ohms, I end up with an answer of 2 ohms here. So 2 ohms is my equivalent resistance. Now the reason why I said that this is kind of overcomplicating it is because I know that the voltage is going to be 12 volts across this 2 ohm resistor, but in truth I actually knew that the voltage back here was going to be 2 ohms, or sorry, was going to be 12 volts for each of these. And the reason why I knew that was because the difference across the battery is 12 volts. And if you are an electron traveling through this circuit, you can only make one choice. You can either go left here and you can go through this, R1, or you can go to the right and you can go through R2. But in either case, as soon as you get through that resistor, you're now on the other side of the circuit. You're essentially at the other side of the battery, and so you've gone through the full 12 volts. So when I came here and I find the 12 volts here, I didn't technically have to do this. I could have jumped right to the voltages here. But since we've made this this choice, let's go ahead and solve for the overall current of the combined resistance here. And in this case, it's V equals IR, so 12 equals I times 2. I must be 6 amps. And that's going to be a good piece of information to have anyway for when we check our work later. Going back, we've already made the decision that the voltage is the same between these two. So I have my 12 volts here. I'm going to solve for my two current values. 12 is my voltage. My resistance is 6, so 12 divided by 6 gives me 2 amps. And then over here, 12 divided by 3 gives me 4. So 4 amps and 2 amps. Now I have all my information. Quick way to check this. We already know that the voltages make sense, but on top of that, since I did solve for what my overall current was coming out of the battery, I got 6 amps. If I look at these two pathways, I get 4 amps of current going to the left pathway here to R1, so 4 amps here, and I have 2 amps here, which means a total of 6 amps is coming in to this parallel circuit, and 6 amps is coming out and going back to the battery. So that checks out between the two diagrams. And that is solving for resistors that are placed in parallel.